Hello students, today we will discuss about half wave controlled converter. Half wave controlled converter, and we'll try to simulate this circuit in PSIM. So PSIM is a new software in which we can simulate all power electronics related circuit. Okay? So we can simulate power electronic circuit, we can simulate various power system based circuit, okay, as well as few electrical circuits also we can simulate in PC. So this is a very famous software that we are going to study in today's lecture. So first of all, what is mean by half wave control converter? The circuit diagram is something like this. It has one transformer. This is a primary of the transformer. Then there is a secondary side. This is a step down transformer, and we are connecting a single SCR. Let's call this as a thyristor T, and here we are connecting a resistor as a load. Okay, so here load is a resistive type. This is a resistive type. Okay, so load is a resistive. So resistive type means bulb. Okay, simple normal bulb is an example of resistive type load, or simple resistance. Okay, this is also a resistive load. So we are connecting such load here, and now we are going to simulate this circuit. Here we are applying a single phase 230 volt 50 hertz supply. So this circuit, we are going to study how this circuit works and uh, how it gives or how it generates the output voltage. So we are interested to measure the output voltage generated at the resistance. This voltage is called as output voltage. Okay, the voltage across this resistive load, we call this as RL, and the current flowing through this, let us denote it as I. Same current will be flowing through the circuit. Okay, and very interesting thing is, which is not shown over here, which is hidden, and this is nothing but gating circuit. So what is meant by a gating circuit? Gating circuit is nothing but the pulses which are essential to turn this SCR on and off. Okay, so this is what the circuit we are interested in. So let us discuss how the waveforms will look like. So at the input, you observe at the input we are applying single phase 230 volt, and the output we are going to get some output waveforms, okay, which is a DC waveform, because we know the SCR is a unidirectional device. First of all, let us note down some peculiar points about SCR. So SCR is a silicon controlled rectifier. Its symbol is something like this. Okay, this terminal is called as anode, this terminal is cathode, and this is a gate terminal. So when a proper gate pulses are applied, then and then only the device is turned on. This is normal semiconductor device, but it is working like a normal diode, but the difference is that there is a gate signal. Okay, so when gate is applied, then and then only this SCR will turn on, and that's why the output generated by this device is called as control. And this is what the difference between a rectifier and control converter. So in case of control converter, the output DC voltage is controlled. Okay, is a control. Control means by changing firing angle, by changing firing angle, by changing alpha firing angle. This alpha is called as a firing angle. So by changing firing angle, we can change the output voltage. We can change the output voltage. We'll see by understanding the waveforms. That's why this is called as control converter. Otherwise, it is just like a normal AC to DC converter. Okay, and a rectifier, as we all know, this is a simple AC to DC converter. This converts AC, pulsated AC into pulsated DC. Okay, now let us understand by means of waveforms how this circuit works. So let me draw a simple schematic to understand here quickly. This is a gate and this is a resistor. Okay, and this point is grounded, and here I am applying a primer. Okay, so at this side there is a single phase AC supply. So let me draw first of all AC supply. So here I am drawing first of all AC signal. So AC signal is something like this. It has a positive cycle as well as it has a negative cycle. Again positive cycle, negative cycle. I will show two cycles. So 0 to pi, from pi to 2 pi, and from 2 pi to 3 pi. Okay, so this is my input voltage, V in, input voltage. Okay, now let's try to draw the output waveform. So let me pick up a different color so that things will be understood very easily. So here I will draw the output voltage waveforms. All these waveforms I am drawing with respective t, or let's say omega. Okay, omega is a radian frequency and t is a time period, or it is f frequency. I can draw these waveforms with respect to any one of these waveforms. So here I have drawn this with respect to omega. Omega is my angular frequency. I can draw this signal with respect to time. I can draw this signal with respect to omega, or I can draw this signal with respect to f, that is hertz. Okay, this frequency is measured in hertz. This is measured in radians per second, and this is measured in seconds. I can plot this graph in these various variable formats. Okay, so my output waveform will be something like this. Now this SCR, you look at the circuit, it will be forward biased during this period. So from 0 to pi, the SCR is forward biased, because you observe the anode of the SCR is at positive potential. The anode of the SCR is at positive potential as compared to cathode, because this side is more positive, this side is more positive. All right, so during this time normal diode starts conducting from 0 because it is forward bias. But in case of SCR, what will happen when the gating pulse is applied? So let us assume here I will pick up one more color, so that let me choose a green color or black color. Okay, so let's say here a gating signal is appearing. So I will show here, this is my gating signal. Okay, a small pulse is appearing. Again a gating signal is appearing here. Okay, it is appearing at regular intervals. Again third gating signal is appearing here. So likewise these gating signals are appearing. So let me denote this as IG. or simply it is called as gating signals or gate pulses. Okay, now when this gate pulse is appearing, okay, then what will happen? Then SCR will start conducting. So although this is forward bias from this point onwards and it should generate a waveform like this, but here at this point only, since the gate pulse is appearing, okay, till this point SCR remains off. Okay, and from this point onwards my SCR starts conducting. So this is the period during which output voltage will appear at the output side or at the load side. Now from this point to this point you observe pi to 2 pi, there is no conduction because SCR is reverse bias, because at this side there is a negative potential and this is positive potential, because this is a negative waveform, negative side of the waveform is appearing, and therefore SCR is reverse bias, as the anode of this SCR is at negative potential and cathode is at positive potential, and therefore there is no question of conduction. This is a very simple case as far as resistance is concerned. Okay, now this period alpha is called as a firing angle. This angle is called as a firing angle, and whatever this pi minus alpha period is called as the conduction angle, is called as conduction angle. Now you can observe here this particular period, that is this period, conduction angle, which is denoted by, let's say, beta, is totally in the is under the control of gating signal. So as gate pulse is reduced, that means if gate pulse is appears prior to this period somewhere here, then there will be a more output voltage. So if alpha is less, okay, less angle, less in terms of, I will say, angle, then output voltage is more, and if alpha is more, then output voltage is less. So there is inversely proportionality relation between the output voltage and firing angle. So if alpha is more, output voltage is less, and if alpha is less, then output voltage is high or output voltage is more, and thereby by controlling gating signal, a pulse signal at the gate, we can control the output DC voltage, and hence these converters are called as controlled converters. Now you observe this cycle repeats here, this cycle repeats here, and therefore I will get this waveform something like this. Okay, so this is from here this is 0, here this is 2 pi, this period is 2 pi plus alpha, okay, and up to this period this is 3. In this way cycle repeats. Okay, now this story is very interesting, as far as this story becomes very interesting when the load becomes inductive. So this case is very simple as far as resistive load. If I consider the load is inductive, then the case is something different. So what is different? So let me illustrate with the circuit diagram once again. So I will go to the next page first of all. So here what I will do, let me choose 1 second. Okay, I will just explain here itself. If my load becomes inductive, okay, instead of resistive. Now suppose my load is inductive, okay, if load is inductive, then what will happen when the SCR conducts? Then the property of inductor is that current through it does not change instantaneously. Okay, so inductor starts charging and it will develop some potential across it, So inductor is charged in the form of flux. Okay, initially it is assumed that it is unenergized. It is unenergized, and the value of inductance is large. The value of inductance is large. So what will happen during positive half cycle? The inductor will charge in this polarity. In this polarity. Now what will happen during negative half cycle? You observe this part of the circuit very carefully. Now here there is an inductor. Okay. Now here positive part is over. Positive part is over. Inductor is charged in this direction. Now what will happen when the negative cycle comes? When the negative cycle comes, the property of inductor is that the current through inductor does not change instantaneously. Although at the input side current is changed, the inductor will not allow sudden change in current at the output side. Okay, and what will it do? It will reverse its polarities. So inductor will reverse its polarities like this. When in the negative cycle starts, then inductor will also change its polarity automatically. So due to which what happens, here there is a negative potential, and here this is a maximum potential because inductor is charged to the maximum value, and this potential is reversed in direction. So obviously this side potential is more negative as compared to this side, and therefore the SCR is still forward bias and SCR will conduct. Okay, so here in this case the current will flow from now inductor in this way, okay, and back to this side, and in this way the inductor is get de-energized. Initially it was unenergized, then it's charged to the full value, and again during the negative half cycle it gets de-energized, okay, making its polarity like this. So during this period, so that we can show in the form of waveforms. So let me illustrate this with the figure. So here during the positive half cycle, let me assume from this point onwards, the charge starts conducting. So this is my alpha. Now due to the inductor connected at the load side, inductor will continue its current, because what will happen, see, at alpha current will start building up in the circuit. Here what will happen, the current will start from this point and ends at this point. Okay, so there is no question of terminating current after. But here what will happen, at alpha the current builds up and at this point when voltage reaches to zero, the current will reach to the maximum value, and then it will extend for a few time after this, and because of which we'll get a negative spike in the output voltage, and therefore this type of waveform will appear in the output voltage. Okay, again for this particular time output voltage is 0, so during this part the SR will remain off, and again for this period from this point to this point onwards this SR will conduct in this way like this. So more the value of inductor, more will be the negative part will appear. Okay, because the charging of inductor will charging and discharging of inductor will take much time. So this is all about the theory. So let us quickly go to the PSIM simulator software and try to understand how this circuit works. So let me create a new file quickly. Okay, now I will select the device. So first of all, from the power, from the source, I will select a voltage source. All right, let me maximize this. I will select this sign, just drag it. Okay, now select SCR. So here there is a SCR, so I will place SCR here. All right, Now select the resistance. Right, so I can select from this side or I can select from here also, component library. Now here if you want to rotate, you just simply right click. Now here I will put resistance. Now I'll require a ground point as well. So here this is a ground point, so I will put this ground point also here. Right, now connect the circuit. So for connection I will just make use of this pencil and I will connect all the components with each other. So SCR cathode is connected here. So observe, this is a resistive load, this is source, AC source, and this is my SCR. Now this ground point is connected here. This is the DC part, so that's why the ground is there. Now let me change the values. So here in AC, peak amplitude is 110 volt, and let me change the frequency to, let's say, 50. Okay, if I want to show this input, I will display it here. This is my SCR, this is my resistive load, and its value is 10 ohm. Now I need a gate signal. So for that I will select a gate pulse, okay, from here, and I will simply put it here. This is my gating signal. Now I will connect this gate terminal of the SCR to the gating signal toolbar tool, and now I want to apply a gate. So I will double click on this. I will make this frequency exactly matching to the input side. So 50 hertz, make this frequency 50 hertz. And this is very interesting, number of points where I want to trigger the SCR. So I need SCRs to turn on at 2 points, one at 0 and another at 180. Okay, at 180 I want to make it off, at 0 I want to make it on. So instead of 0, you change this angle. So let me make this angle as a 45 degree initially, and that's all. Now I will select some probes to measure the voltage. This probe is for measuring the voltage at the input side. This probe is for measuring the voltage at the output side. And I will select the current probe. I will put it here. Alright. So I place the current probe here. Now I will rename this. So this V2, instead of V2 I will call this as VI, and let me click on this display tab, show that it is displayed here. Alright, and this is my output. So I will click here and change it to VO. Click on display so that it will display, and this is my current circuit. Okay, now for simulating, just go to the simulate, click on simulate control, and how many cycles I want to display, that I have to give here 0.01. I want to display, let's say, 3 cycles. So I will give 30 millisecond time period, so 0.03, and this is the time that I need to give over here. Then click on this side. Now you are ready for simulation. Simply click here, run this simulation, and now you can very easily observe your output voltage. So initially let me observe my input voltage. So click on OK. See, 110 volts, and I am interested in 3 cycles. I have seen here 3 cycles. Okay, let me add to this graph one more graph, that is of output. So add here. Now click on OK. You see here, this is my firing angle at 45 degrees. I have changed it. Okay, so from 45 degree onwards my SCR conducts till this 180 degree. During this negative half cycle, SCR is totally off. Again, for this third positive half cycle, from this 0 to this point, SCR is off, and from this point onwards again cycle repeats. Okay, so this is my output voltage, and let me add a current waveform. Since the load is resistive, alright, the current has same shape as that of the voltage you see here, but only the magnitude is somewhat different. Here you observe this is around 110 volts, whereas current is around 11. Okay, because you see the output voltage divided by resistance is the current. Okay, so that's why current value is around 11 amperes. Then the output voltage is around 110 volts. This is input voltage. Now for testing purpose, if you go to this here and if you change this firing angle to, let's say, 90 degree, or some more angle, like let's say 120 degrees, okay, and if I resimulate it, okay, then see here it is more than 90 degree. This is 90 degree exactly, more than 90 degrees, so it is 120 degree. So increasing firing angle, increasing alpha will reduce the output voltage. This is clearly observed. Now I can have some analysis and measurements also. So I can measure the voltages and current also. Here you can see output voltage is around 9 point somewhere, something like this. So if I open this, double click on this, and click here, then you see it is around 98 or 100 volts or so, something like that. This is output voltage. So if you calculate by using formula for 120 firing angle, this is the output voltage, right? uh, and same is the case for current. You can click here, double click here, okay, and this is 9.89. so initially it was 11 amperes, now it is reduced to 9.89 amperes. So in this way, as alpha is increased, alpha is more, output voltage is reduced. Now let me illustrate it with the help of inductive load. So let me change this resistor. Instead of resistor, I will put inductor. Let me choose the inductor and let me place it here. Okay, cancel this, select this and delete it. I'll change the value. I want to make this very large, so I will make this inductor, instead of 1, it's 10 millihenry. Okay, I will change the firing angle. Initially, let's say it is 50 degrees. Okay, click on OK and run the simulation. Now here you will observe, during this part, here at alpha is equal to 50, the SCR starts conducting, but here at 0 the SCR doesn't stop. In the initial waveform you observe, from this point onwards the SCR was off, but here you will observe that the output voltage will be generated in the negative side as well. So by placing inductive load at the output side of the rectifier or the converter, it reduces the efficiency. So inductive load will reduces the efficiency. In the next session, we'll discuss the effect of freewheeling diode, in which by connecting a diode across the load, this effect is nullified. So that we'll see in the next class. Okay. So before I close, let me illustrate it one more simulation. So here I will first of all remove this current, so that I will remove this. Okay. Now I just want to, or I will close this and I will just increase the value of alpha to, let's say, 90 degrees. Okay, and let me see what is the effect. So when I run this simulation, now I will just add output voltage, because I know the shape of input voltage. I am not concerned about input, I am just interested in output. Oh, see carefully, very beautiful waveforms are appearing. So at 90 degree SCR starts conducting, and at 180 degree, instead of SCR getting off, it will still go on continuing conducting the current in the negative half as well, because inductor changes its polarity, and because of which we get a negative output voltage as well. Now you observe, if you compute the average output voltage in this case, the average output voltage will be 0, because the positive area is exactly equal to negative area. If you observe the current waveform here, let me select the current, then see here from this point onward, initially current was starting from 0. Now here in this case, the current is starting at alpha, and then it reaches to the maximum value, okay, where the voltage is getting reduced to 0. So current is maximum, and then current starts decreasing in negative direction. okay, when the voltage reaches to the negative, okay, and at this point the current becomes zero. So it is very easily uh, we can understand the operation and behavior of inductive load in case of single phase controlled rectifier. So this is all about. In the next class I will explain the effect of freewheeling diode and further details. Thank you.